Hi, welcome back to CS560. So from this lecture on, we are going to talk about some advanced algorithms, some advanced graph algorithms. So in general, we will cover two types of problems or two types of algorithms. The first type of algorithm solves the minimum spanning trees problem. And the second type of algorithm solve the single source shortest path problems. So as a comparison with the previous lecture about elementary algorithms on a graph, uh, in general, the difference is that the so-called advanced algorithms, they focus on or operates on more on the edge side of a graph, or on the edges part of the graph. And so the edges in this lecture, the edges of graph are weighted. So the graphs we talk about in the advanced algorithms lecture here are more like weighted graphs that each edge has a associated numbers that indicates the weight. But previously, when we talk about the elementary algorithms, the edges are not weighted, or at least we don't consider the weights of the edges, and we just ask questions about whether the vertices are connected or not. So the previous elementary algorithms, they focus more on the vertices in the graph. Okay, so but that is not to say that the elementary problems is not important. They are still important. So they provide some basic tools like BFS, DFS to traverse the graph, which will still be useful in a lot of more advanced problems. Okay, and as I said, from this lecture on, the advanced problems that we focus on are they focus on more on the edges. So we will need to take into account the weight information of the edge. So the first type of problem that we cover is the minimum spanning trees. Okay, so this is a new terminology, right? So, but it is a pretty common problems that you will certainly know about if we use some introductory examples. So here we use the example of circuit wiring problem. Okay, so this problem is about electronic circuit designs. Okay, so in this design process, we often need to make several pins on the circuit's equivalents by wiring them up or wire them together. Okay, so on the circuits we have a lot of metal pins, and if we wire them together, their voltage will be equal, right? So this is the important process of designing a circuit. So in order to say if we have n pins, we'll need to use n minus 1 wires to make all pins connected or connected to each other. Okay, so that is a complex problem because different ways of doing this arrangement will result in different costs in terms of the total amount of wire or total length of wire. Okay, so of course we want to use as small amount of wire as possible, or we want to make the shape of the wires to be as simple as possible. Okay, so for example, in a circuits like this, and if you consider all the red large circles as a pin, okay, and all these red lines as the wires between those pins. So of course, these type of arrangements make all the pins interconnected. So all those big red circles, they are of equivalent voltage levels because they are connected by wires. But this is, of course, not an ideal way of doing this arrangement because there's a waste of wires. Some of the wires are non-necessary. Okay. So as a result of a simplification, we can remove some redundant wires, but still keep the pins interconnected. So like we're removing these short wires here and the wires here. So as a result, we use less amounts of wire, but still we satisfy the function or satisfy the goal of connect all the pins. Okay. And still we can do a further simplification by replacing these longer wires with these shorter wires, but still maintain the interconnectivity among all the pins. Okay, so this is basically what this circuit or wiring problem about. Okay, and in order to solve this problem technically, we can describe this problem with a minimum spanning trees. Okay, so we can describe a circuit with a graph data structure. Okay, and we use a connected and undirected graph. Okay, so we don't consider the directions of the wires. As long as two pins are wired, the direction doesn't matter because the electricity goes either directions. Okay, so we call a graph is connected. So this connected concept is pretty similar to the ones that we introduced in the strongly connected components problem, SEC problem, right? So we say a graph is connected simply by saying that if any pair or every pair in that graph, they are reachable towards each other, then we say it is connected. Okay. So using the graph representation of a circuit, then the vertices, the set of vertices, V is simply the set of pins, and E, the set of edges, is the set of all connections between pairs of pins or set of wires between pin pairs. Okay, so because this is a optimization problem and longer wires cost us more metal material and more money, right? So we can simply assign each edge a weight to specify the cost. Okay, so for each edge that connects the two pins from U to V, we give it a weight W. Okay, so this W between U and V is the cost of the wire that connects the pin U to pin V. Okay, so and this weight is a real number. Okay, and our goal is to find a subset, and this subset is not a cycle. It doesn't contain a cycle, so it's called a cyclic subset. So this subset T is a subset of E. Okay, so T is a subset of edges. Okay, we're not talking about vertices this time. We are talking about a subset of edges that can connect all the vertices or pins. And that subset satisfies this constraint. The total weight of this subset needs to be minimized. Okay, so the total weight is a summation of all the edges within that subset. Okay, so this is using graph data structure to help us represent the circuits. We can basically converts this problem into a optimization or minimization problem to find a subset of edges within a graph structure. Okay, so we haven't explained why this problem is called a minimum spanning tree problem. Okay, so far we are talking about a subset T of all the edges in the graph. So it's not a we haven't introduced the tree yet. Okay, but this is a straightforward step because we want the subset T to be acyclic and it connects all the vertices, right? So it must be a tree. Okay, so if there's a cycles in the subsets, then there's no hierarchical structure from the root to all the children nodes. So if it's acyclic, there's no cycles. That's the roots. We can always define the roots of the tree, and then we lifted that root vertex up, and all the other vertices become the children or descendants of that root. Okay, so this is a natural step that as long as we want to find acyclic subsets, then it can be represented by a tree data structure. Okay, so this tree is called a spanning tree because it spans the graph G, because it connects to all the vertices, to all the corners of the graph. So that's why it's called a spanning tree. And that's why we can we can call the problem of finding the tree the minimum spanning tree problem. Okay, so here the minimum, the prefix minimum or the adverb minimum means that we want to find the spanning tree that has the minimum weights. Okay, so the minimum doesn't refer to the number of edges, but the total weight of edges. Okay, we're not talking about we want to find a subset of the edges that has a minimum number. No, that's not true. We want to have the subsets of edges that has the minimum total weight. And theoretically, all the spanning trees have exactly the same number of edges. Okay, because we want connect all vertices, and the number of vertices is fixed, right? As long as we want to connect V vertices, it is a mathematical fact that we must use at least V minus 1 edges. Okay, so this is a theorem that you can go through by yourself in the textbook. Okay, so the spanning tree, the minimum spanning tree must have exactly V minus 1 edges. Okay, and that is also the number of edges in the tree, in the resulting tree. Okay, so in this particular example here, we have vertices from A to I, A, B, C, D, E, F, G, H, I, right? And all the weights, all the edges, we have different weights associated. So if you look at the shaded edge, okay, so the shaded part includes the edge AB, BC, CI, CF, GF, GH, and DE and CD, right? So this is a subset of all the edges, because the other unshaded ones, BH, AH, IG, they are not included in this subset. So this is an example of the spanning tree, okay, because it is a subset of the edges and it connects all the vertices in the graph. Okay, and this is also a minimum spanning tree because the total weights of the shaded edges here, if you sum them up, it'll be 4 plus 8 plus 7 plus 9 blah 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 and the summation is 37. Okay, and this is a minimum spanning tree because this total weight is minimized. Okay, and you can examine it yourself, and this minimum spanning tree is not unique. This is important, okay? We're not saying that given a connected graph, we can find the minimum spanning tree, but we can find a minimum spanning tree because a minimum spanning tree is not unique. Okay, for example, in this example, if you remove the connection, remove the edge BC, but add another different edge but with the same weight AH, it's still a minimum spanning tree. Okay, because the weight doesn't change. You remove an 8 plus an 8, and all the vertices are still connected, right? So the minimum spanning tree is not unique. Naturally, the next question is how we find the minimum spanning tree of a graph. Okay, so here we use the word growing. So we typically, when we want to find the minimum spanning tree, we usually take a step-by-step or incremental style by starting from some empty set or very small set of edges, and then gradually grow the tree by adding one edge at a time. Okay, so this is a typical style that we follow. So we will first define a generic method to grow an MST or minimum spanning tree. And then this generic method is, you can think of it more of a virtual function or virtual method that we only define some basic principles that can successfully find an MST. Okay, but it is not actually a implementation with the pseudocode that works. Okay, so based on that generic method, we will then go on to define two actual algorithms based on that generic method. Okay, so the first one is Kruskal's algorithm, and the second one is Prim's algorithm. So they both follow the generic method, but they use a bit different strategies when they implement the algorithm. Okay, so now let's look at this, what this so-called generic method is. Okay, so we here provide a procedure called GENERIC-MST, and it takes inputs a graph G and W. So the W records all the weights of the graph, of the connected and undirected graph. Okay, so one assumption is that the input graph is connected. Okay, we assume that all the vertices in that graph are reachable from each other. So that means the MST does exist. Okay, and also we have a weight function W that provides all the weights information. Okay, so this is a pretty simple line of procedure, because it first initializes a set into empty sets. Okay, and then you use a while loop to incrementally grow that empty set, and finally it will return that empty set as the MST. Okay, so it uses a while loop if that's to check whether A is a spanning tree or not. Okay, and then if not, it will find one edge that is currently safe for A. Okay, and we don't know what safe means, so we'll keep it for now. We'll just leave it here. So we'll choose a safe edge for A, and then we'll grow A bit by including that safe edge into A by this union operation. Okay, so this union operation and this assignment means that we incorporate a new edge into A. Okay, so it basically manages a set and maintain, and this there's a following loop invariant maintained. So prior to each iteration, the set A is a subset of some minimum spanning tree. Okay, so what basically this generic method does is to, at each iteration of the while loop, it find an edge to add to A, and this edge doesn't violate the loop invariance. So in a sense that the resulting new A, the union between the current A and the new set, the new edge, is also a subset of an MST. Okay, so and such an edge is called a safe edge for A. Okay, so that also implicit means that not all the edges are safe for A. So there's only a small some edges can be added to A without violating the loop invariant. And the loop invariant is simple. It simply means that A is a subset of MST. Okay, so whenever it reaches the point that A grows into a full MST, then the while loop will terminate and return the A. So that's basically how the generic method works. So of course we didn't touch all the details about how to find the safe, how to define the safe edge, right, and how to find the safe edge. So we'll go through the details in the following slides. So the trickiest parts of this generic MST procedure is at line 3. So how do we find a safe edge? So in order to implement a actual algorithm, we need to define what a safe edge is properly. Okay, so now we'll shed more light on how we define a safe edge in a graph with respect to the current subsets A. Okay, so in order to do that, we need to define a series of concepts. So let's start from the concept of cut. Okay, so a cut is a way to partition the vertices of a graph. Okay, so a cut, if we write a cut into parentheses S and V minus S, so this cut operation divides all the vertices V in this graph into two parts. The first part is the set of S, and the second part is what's left, V minus S. Okay, so for example, in this graph, the vertices are colored into black and white. So the black part, S is a subset of vertices V, so it includes A vertices A, B, D, and E. So on the other side of the cuts, V minus S is a set including H, I, C, G, F. Okay, so a cut is a partition with respect, or partition on top of the vertices. Okay, and the other, in this example here, we use the black color and the white color to indicate the two parts. Now, so in this plot, you don't need to pay attention to the edges yet, because a cut is defined onto the vertices only. Okay, but in the next slide, we will define other two concepts that are related to the edges in the graph. So now we'll talk about the concepts of cross and respect. Okay, so we say that an edge from vertex U to V crosses the cut if one of its endpoints U is in S and the other point V is in V minus S. Okay, so that is a straightforward definition. So because the cuts divide all the vertices into two parts, S and V minus S. So if an edge, the two endpoints of an edge exists in the two sides, then we say the edge crosses the cut. Okay. So in this example here, the edge from A to H, so if we look at it, it has a cross with the cut. Okay, so first of all, the cut is an imaginary, is plotted as an imaginary line that separates all the vertices, right? So in the actual view of a graph, it doesn't exist. It's just a abstract concept. So AH, the edge AH crosses the imaginary boundary or cut, and BH, BC, CD, DF, and FE, they all cross the cut. They cross the boundary. So that's the second concept, cross. And with cross defined, then if we look at, now let's look at a subset of edges. Okay, so in the example here, we have a shaded edges, and let the set of the shaded edges to be our subset A. So A is a set of edges that include AB, HG, GF, CF, and CI, right? So it is included here. It has 5 edges. So one of the property of the edges in A is that none of them, as you may already notice, that none of the edges in A cross the cut. Okay, so we say that the cut demonstrate here respects the set A, respects the shaded subset of edges. Okay, the shaded edges are called A, and then we say the cut respect the set A because there's no edge in A crosses the cut. Okay, so you can imagine that when I draw the cut, if I pay respect to a subset A, then that means I carefully draw the cut without crossing any edge in that subset A. Okay, hope that help you better understand where the word respect comes from. Okay, so that's cross and respect. Okay, and now let's look at the last concept that we need to define. So now let's define the so-called light edge. So light means not heavy, it's very light in weight. Okay, so we call an edge a light edge crossing a cut if its weight is the minimum among any edges crossing the cut. Okay, so given a cut of the graph, among all the edges that cross the cut, we choose the edge that has the minimum weight, and then we call it the light edge. Okay, so in this example, we have the weights. We have 1, 2, 3, 4, 5, 6 edges that cross the cut, right? We just look at their weights, and it shows us CD has the weight 7, therefore it is the unique light edge crossing the cut. So there could be multiple light edges when there's a draw or there's a tie of their weights. So in that case, we just can randomly select one edge as the light edge. So that's why here we say a light edge, but not the light edge, because it could be not a unique light edge. Okay, so light edge is actually more generally used concept. So we can, so this in our case of defining the light edge, we define it in a sense that it should cross a cut. Okay, but we can also define all other kinds of light edges with respect to other properties. So in a more general way, we can say an edge is a light edge satisfying a given property if its weight is the minimum of all the edges that satisfy the same property. Okay, so in our case here, the given property is that the edge should cross a cut. Okay, so that's all the concepts needed in order to define a so-called safe edge. Okay, so now using the concepts we have defined above, we can put together the rule for finding the safe edges that is used in the generic MST method or generic MST procedure. Okay? So the rule for finding safe edges is given by a theorem. Okay, so this theorem says, given the graph which is connected and undirected and with weights, okay, and let A to be the subset of edges that include some minimum spanning tree for the whole graph, okay, and let SV minus S be any cut of the graph that respects A, okay, and let the edge from U to V be a light edge that crosses the cuts S and V minus S. Then, if we can find such a light edge, then this edge is safe for A. Okay, and it means that if we add that edge U to V to A would still be a subset of the minimum spanning tree. Okay, so the full body and how it is proved, it can be found in a textbook. Okay, so having a first glance of this theorem, of course we need to use the concepts cut, respect, and the light edge and the cross concepts that we used in the previous 3 slides. Okay, so it makes the requirements of finding a safe edge pretty clear. Okay, so because the algorithm is to grow a minimal spanning tree from scratch, from empty. Okay, so A is a growing subset of edges. Okay, so with respect to that subset A, so if we can find a cut, it could be any cut of the graph that respects A. So when we draw the cuts in the graph, we be really careful and don't cross any edges that are already in A. Okay, and after we draw the cuts, then we focus on all the edges that cross the cuts, and we will choose the light edge, which is the minimum, which is the edge that has the minimum weight among all the edges that cross the cut. Okay, and that edge is exactly the one that's safe for A. Okay, which means it can be used to grow the subset A for further step. So that's what we have for defining the safe edges using this theorem. Okay, so it'll be an interesting process to go through how we prove the theorem. So in the next few slides, we are going to go through that steps. And if you need more detailed explanations or demonstration, you are recommended to read the textbook. And these are really helpful to understand why the GENERIC-MST is a effective algorithm that's build a minimum spanning tree. In order to prove the theorem, we will first let T to be some minimum spanning tree that includes A. So let T be one example of the results MST that we want. And we assume that this MST minimum spanning tree T does not contain the light edge from U to V. Okay, so because if it does include UV, then we are done with the proof. And our goal is to prove that if we can construct another minimum spanning tree T prime, which is different from T, but that T prime includes not just A, but also the light edge from U to V, then we can actually showing that the edge UV is safe for A. Okay, so just remember the goal is to prove that the edge UV is safe for A. So this statement is what we want to prove in the theorem. Okay, so if we follow the logic, because we assume that the first minimum spanning tree T does not include UV. Okay, so that means if in a spanning tree of a graph, and one edge is not included in that spanning tree, which means if we let UV to be in that, to add it to that tree, then it must form a circle with the edges on the simple path from U to V in T. Okay, so let me put it another way. So UV is currently not included in the final MST, final minimum spanning tree T. Okay, so all the edges and all the vertices, all the edges, you can imagine it as the final minimal spanning tree T, and only those shaded edges are the subsets A. Okay, so A is a subset of T. So because T is a spanning tree of the graph, okay, so it cannot be acyclic. Okay, there's no cycles in a tree. Okay, so because T doesn't include UV, then according to the definition of the minimums of the spanning tree, because any two vertices in the spanning tree are reachable from each other. Okay, so because U and V, the direct connection between U and V is not included in this final tree, then there must be some other path that leads from U to V, indicated by this lowercase p for the path, right? So if this is not the case, if there's no such a path, then the whole spanning tree is not a spanning tree because the 2 points are not reachable, right? Okay, so that's what we must have. The simple path P must exist in the final tree. Okay, and based on the description of the theorem, the edge from U to V is on the opposite sides of the cuts. Okay, so that means at least one edge in the tree, in the spanning tree, lies on the simple path P and also cross the cuts. Okay, because the U, the P, the whole path from U to V, plus the edge UV, it forms a circle, it forms a cycle, right? And when we draw a cut that cross the whole graph, and we know that that cut already crosses UV, then it must crosses another cut in that cycle, right? Otherwise, the cut will not establish, the cut will not exist. So if the cut that crosses UV exists, then it must cross out of the cycle through some other edge. Okay, so in this case, we imagine that, we just assume that X and Y is such an edge, okay, and XY is not in the XY is not in A, okay, because we also assume that the cut that we draw respects A. Okay, so that's why the edge from X to Y is not shaded. Okay, so let X and Y be that edge that also crosses the cuts. Okay, so now we can simply remove the edge X and Y so that the tree is broken into 2 components, and we add the edge from U to V to reconnect the 2 components, and the result will be a new spanning tree, right? So the operation of removing XY can be indicated by this minus a set that contains X and Y, the edge X to Y, and a union, following a union operation with a set that contains the edge from U to V. Okay, so this is how we obtain a new spanning tree. So note that we don't know if this new spanning tree is a minimum spanning tree or not. We just know that if we remove the edge XY, the original tree will be broken into 2 parts. And then by connecting U and V, by adding U and V to the by connecting the 2 components through the edge U to V, we are creating a new spanning tree. Okay, so our next step is to show that the T prime, the resulting new spanning tree T prime, is also a minimum spanning tree. Okay, so since U and V is a light edge, the edge from U to V is a light edge. That's what our theorem states, the description of the statement of the theorem. So we know that U and V is a light edge. It has the minimum weights among all the edges that cross the cut, because currently xy is also a cut that is also a edge that cross the cut. So the weight of uv must be smaller than the weights of xy, because uv is the light edge, and we don't know about whether xy is a light edge or not. So it must satisfy this less than and equal to inequality relationship. Okay, so now it's clear that the total weight of the new spanning tree T prime is the weight of the original tree minus the weights of xy, which we excluded from the tree, and the plus the weight of uv, which we included into the new tree. Okay, so by minusing the weight of xy and plus the weight of uv, because this one is smaller, then we must have the total weight of t prime should be smaller than or equal to the weight of the original tree t. Okay, so as we know that t is already a minimum spanning tree, then if the weights of that means the total weights of the spanning tree cannot be smaller. T is already a minimum spanning tree, so that means the total weight of T prime must also be greater or equal than or equal to T. So combining this inequality with this inequality, we must have that T prime should have the same total weights of T, which means T prime is also a minimum spanning tree. Okay, that said, because T prime is a minimum spanning tree, we have shown that the edge from U to V is safe for the current subset A. Okay, so that's basically how we prove the theorem, using the properties of spanning tree and minimum spanning tree, and the properties of a cut that respects the current subset A. Okay, so given the proof of the theorem, we are able to show that the generic MST procedure is a correct procedure, is a correct one that will help us grow a minimum spanning tree in the correct way. So now let's look at how this generic MST procedure runs in general. Okay, so when this procedure runs, the subset A is always a cyclic. So at any point, if we consider all the vertices and the subsets of the edges A together as a new graph G subscript A, then this subgraph is it contains a lot of trees. It's itself a forest, and each of the connected components in this subgraph is a tree. So as the currents, the bottom left plot shows, we have two components in the current subset A. Okay, the first component is this one, right? And the second is this one. Oh, and also including this vertex as a component as well, and this vertex as itself is a component as well. So it is a bunch of trees, and actually it's a forest. So any safe edge for within A that connects this can connect distinct components within this subgraph. So this edge can connect this component with this component, right? So, and this whole while loop will execute exactly v minus 1 times, because the minimal spanning tree for a graph that has v vertices, it requires exactly v minus 1 edges. So because the current subset A grows from empty sets, so in total it will run v minus 1 times. Okay, and initially when A is empty, there are v trees in the subgraph, because each vertex is considered a standalone tree. Okay, so that's why we have v trees, and each iteration will reduce that number by 1, which means we are combining two components together by adding a safe edge. Okay, so when the forest contains only one single tree, then the method will terminate, and that single tree is exactly the minimal spanning tree that we want. Okay, so next, we have introduced the generic method for growing a minimal spanning tree, and we have known that the key is to first have a cut, define a cut onto the graph that respects a current subset A, and then we try to find a minimum. We need to find the safe edge, okay, that will grow the current subset A incrementally. Okay, so in the next lecture, we will introduce two algorithms that elaborate on the generic method, Kruskal and Prim. So these two algorithms, they use the same basic thoughts of generic method, but they use different ways of defining the cuts, and they use different rules to determine a safe edge. Okay, and so that's so much for today's lecture, and I will see you next time.